Today, I will be showing model execution with Rhapsody. And my focus is on UML and C++ code generation and how objects collaborate with one another. Rhapsody supports model execution for UML and SysML and other UML-based languages. The mechanics that we use in Rhapsody are the same regardless of which modeling language or whether or not you're generating C, C++, Ada, or Java code from Rhapsody. I'll be using this very simple reference model here. The intent again is to show different modeling notations and techniques in Rhapsody. We see that there's a couple different objects here. SS1, that's subsystem 1, is communicating with subsystem 2 using two different types of ports. At the top, we've got two standard ports here. And each port, that's a named interaction point, and they're typed by an interface. So SS1 provides a service. It says that if you call start flow on this port, it will handle that call to start flow. On the other side, SS2 has a required interface, and it says that, well, if you're going to go ahead and hook up to me at my port P1, and when I call start flow, you need to be able to manage it. So we've agreed on this contract here between SS1 and SS2. At the bottom here, we've got flow ports. The way this works is you notice that there's a rate flow port on SS1, and SS1 also has a rate attribute. When rate attribute gets set, that data is going to flow out the flow port, and on the receiving end on SS2, its port name is F1. It has an attribute of the same name. So the way this demonstration works is SS2 is going to call start flow. Start flow will set the rate attribute, and then data will flow across back over to SS2 and populate the F1 attribute. So we can see that these objects here, using Control L on my keyboard to locate that model element in the browser, I see that these are objects. I can very quickly see the code that gets generated from them. These happen to be generated by value in Rhapsody, and those of you that know code generation in Rhapsody know that there's a lot of different ways they change how the code gets generated. And we see that SS1 has a start flow operation. And start flow has an implementation. We're going to see that model execution highlights a problem with this particular operation. Then we'll fix that later on in the demonstration. All right, well, let's get started and see how that looks. I'll switch over to an animation configuration. In Rhapsody, we have a component. Now that's an overloaded term for sure. Components in Rhapsody, they are generated as an executable or a library. And in my example here, I've got two different configurations. One has animation turned on and one has it turned off. And you can see on the settings tab of the configuration that animation is turned on. There's another type of instrumentation called tracing, and on that other configuration, it's actually set to none. There's an advanced button in here as well, and I've got enable operation calls set to all. Now that's going to let me call the triggered operations on the state chart, as we're going to see here shortly. Another little tidbit here is that the sequence diagram that we're going to be looking at, I just created one. I call it execution. It's just got the instance lines that I'm interested on it. And I've got a property set on this to always launch this sequence diagram when I run the application. So let's run the application and see what happens. I'll make a little bit of space here. There's an animated version of that sequence diagram I just showed you. I'm interested only in the communication between SS1 and SS2 at this point. And we'll start this running, and I see that SS2, okay, great. Looks like that's actually running here. And I can see also in the browser that we do have an instance of SS1 that's been created, and that's because it's a global object, as we saw before. And what I'll do is I will open up the feature dialog for that so we can monitor the attributes. Let's open up the state chart for SS2, the animated version of that state chart. Get rid of the browser, make a little bit of space, and look at these side by side by tiling vertically. Okay, we can make a little bit more space right there. And what we can do is see that we've got the state chart for SS2. It's initially in the off state. By injecting an EV start event, I can see what happens. It will move to the running state and a timer will start running. Let's pause this now and then we can scroll up and actually see what that did. So I told it to start running. It transitioned the SS2 object, transitioned from the off state to the running state. It started a timer, a 2-second timer, 2000 milliseconds. When it matured, it sent the timer event to the SS2. The code sent the timer event to the SS2 object. That caused the transition, caused some source code to execute, which goes, loops through and is updating this Y attribute, and the Y attribute would be the same value every time that the transition occurs here. It will be the same value twice in a row every time the transition occurs. That value then is sent out through the port calling the start flow operation. That's been captured by Rhapsody on the sequence diagram. Start flow sets the rate attribute, and when that rate attribute gets set, data flows out the flow port. Now, we can look at this though, and we can say, well, that's not really what I want. I don't want data to flow out the flow port when data hasn't changed. So there's a way that we can tell Rhapsody to only flow data when the data has changed. We can, on the flow port, open the feature dialog for that. We see this invoke relay property and set it to upon value change. We'll save that, stop the animation, and tell Rhapsody to generate the source code, make it, build it, link it, and run it. So we've done that with one click. Make a little bit of space here. Again, tell Rhapsody to start running. We can inject that same start event and see what happens now. See if that actually behaves like we expect it to. So it actually does. Look at that. So what's happened now is the start flow operation is being called just like it was before. The rate attribute is being set just like it was before, but Rhapsody has generated source code that flows the data out the flow port only when the data has changed. So it's keeping track of that in the generated source code. Let's take a look at our second object model diagram, which shows the same two objects that we saw before, but also a third one. Now the difference here is that we're showing communication with a standard association. We could also do aggregations and compositions as well. But what we have here now is SS1 is able to communicate with SS3, it has an association. SS1 knows SS3 by the name it's SS3, and SS3 knows the object of SS2 by the name it's SS2. Rhapsody is generating all the source code for that, linking the proper objects together, doing that all for us just with the click of a button there. So let's run again. This time we're not going to remove any of those instance lines. Let's see what it looks like now when I run this. Well, let's see. We've got SS2 being created still in the off state. Let's open that up there. Okay. And then SS3 actually has an activity diagram added to it. Now, software developers don't often do this, actually using activity diagrams here, but systems engineers that are using SysML, they will often do this. So let's look at these side by side again, like we did before. And again, same state chart on the top here for the SS2. SS3 on the bottom here has this activity diagram on the left, which is using a token flow semantics. So the way this is going to work now is I'm going to start running this scenario by injecting the EV run event into SS3. It will cause this token to be delivered. It'll then send an EV start on over to SS2. That's the EV start that I injected before, and then we'll start this transition, okay? And then what's going to happen is when start flow is called, we're going to see this time that there's actually an EV new event being delivered to SS3. So it's actually being sent from that start flow operation. All right, well, enough talking. Let's take a look at this and see what it looks like. Again, we'll inject an event, close this down, and see how the model behaves. So we'll let it run a little bit, and then we'll pause it and take a look at what this looks like. All right, so it's actually ended already quite quickly, at least the activity diagram did there, and we'll make this bigger, scroll up to the top, and assess how our software is working. And that is why we're using model execution here, typically as a software developer, to take a look at things, make sure that it's behaving like we expect it to. So sure enough, just like before, we can see the start flow operation being called, the data flowing. Also, EV new data is being sent from SS1 on over to SS3. So that looks pretty good too at this point. And then it continues on, and data is not flowing, but we've got a problem here that the sequence diagram is showing us, that model execution is showing us, that EV new data is still being sent on over to SS3. And that's not really our intent. EV new data, the name implies, of course, that is new data. Well, there is no new data here. So we want EV new data to be sent only when there really is a new data value. So we need to make a change to our model. We saw earlier that start flow sets the rate and it sends that EV new data event on over to SS3. And this is the problem. We don't want it to be doing that at all times. And as I said, there's many different solutions to every problem. And I will show you just one solution to this particular problem. And part of my reason for doing it this way is to show you just some other notations in Rhapsody as well. Okay, so I'm going to comment that out so it doesn't send that data event right now. And it turns out that I'm not going to need this link anymore. And my SS2 class had an association. I'm not going to need that anymore for the solution that I'm going to implement right now. But I am going to make this now symmetric. And to do that, we need to change the association to actually use both ends. And as I do that, then the link automatically will change for us as well. So now SS1 can send messages to SS2. SS2 can send messages or call operations on SS3. So let's then update the SS2 state chart. I'll put a super state around the previous state chart. Now just call it, we'll just call it active, something like that. Okay. And what I want to do now is I will add a reaction in state, or internal transition in state, as it's also called. What I'll do is I'll create a trigger. We'll call it, we'll select CHF1. And on this, I'll use some of that code that I had used before. Because now it turns out that I can communicate with SS3. That same line that I removed from the operation before, I'll add here. And this CHF1, that means change F1. That is an event that Rhapsody will call if it's been added into the model whenever that attribute has changed. So the way this is going to work now is the start flow operation is called. Only when data has changed, the rate's going to flow over. It's going to be received as F1. The generated code then will then call the change F1, the CHF1 event. Actually, it'll send the event that'll be consumed, and then the state chart, regardless of whether or not it's in the off or the running state, will actually execute that CHF1 and then send the EV run scenario, or EV new data that is, event on over to the SS3 object. Let's save the model and generate make run. It's generating the source code. It is compiling and linking it, and then it'll run, and we should see that this is working for us. Let's inject that same event that we did before to actually run this scenario and see how things look. It's different for sure. All right, let's pause that and let's scroll up and talk about it some. So we injected the EV run scenario into the SS3 object. Again, that's the one in the bottom right here. And let's just look at these perhaps side by side, and we can talk about it more clearly. All right, so as we then scroll down, we can see that sure enough moved, that sent the EV start event to SS2, moved it into the running state. The timer matured just like before, data is flowing just like we saw before. The difference now is when that F1 data, when that rate is received at the F1 flow port, Rhapsody calls or sends this change event operation. So it's sent, then the state chart moves into, the object moves into the running state, and after that, it's actually received. When it's received, SS2, the object, sends the EV new data event on over to SS3. And then when it does that, it actually starts a new timer and it matures, and this all starts over again. But what we notice now, though, is that the EV new data is sent only once for every data value. And that's exactly how we want this to behave. So we've used model execution to test our software. We found problems with the software that, yeah, we could have probably solved with some IDE where we're stepping through the source code or putting in print statements. But this is a simple example with just 3 different objects. So imagine if you had a very large application, many objects, a hierarchical system, multiple threads, perhaps multi-cores. Rhapsody can handle that for us, support multiple threads and multi-cores, and actually color code the messages that are appearing on the animated sequence diagram for the different cores. A lot of capability there. This is just a quick introduction. And as I've said before, Rhapsody also supports this for SysML and the other UML-based languages. For the SysML folks, you'll be interested in knowing that proxy ports are supported as well. In fact, I've got a copy of this same model with proxy ports in it. So let me know if you're interested. I'd be happy to set you up with that. Thanks for watching and take care.